It's a nitro-substituted compound, and there had previously been no methods developed for doing deuteration exchange on compounds with very strong electron withdrawing groups. And over the course of the past 15 months or so, through much gnashing of teeth and effort and sweat and things of that nature, Alex has finally succeeded in developing a technique for doing this. And so one of his successors will now be using that method to try to prepare enough of this compound that we can send it off to our neutron scattering colleagues. And so not flashy, not splashy, but the result of some very, very dedicated and intensive labor over the course of more than a year, just to try to generate the starting material to be able to produce these materials. And this is pretty typical of Alex's level of work and dedication. Today he'll be talking about a couple of new compounds that he has synthesized that are of interest to us for their magnetic properties, and without further ado.
Thank you for that kind introduction. So I work in Professor Turnbull's lab. He works in collaboration with Professor Villani's lab, in which we study molecular magnetism of materials with a strong focus on the magnetostructural correlation, which is the theory that the physical structure of a material is directly related to the magnetism of the material. With this in mind, we wanted to design 2D anti-ferromagnetic layers, and the interest in this is that high-temperature superconductors have the same topology, and we would like to probe this type of topology and the magnetism of these materials using moderate exchange materials. So the 2D, I've sketched the diagram up here for the 2D layer in this top left, but there are also other common topologies, and there's ladder, chains, dimers, and honeycombs. M in this case is a magnetic ion, and the lines in between the M's are not bonds. They are simply interactions in the super exchange pathways. And there are two common super exchange pathways that we study in our labs, and that's the bi-halide bridge and the two-halide bridge. The main difference between the two is the number of non-magnetic atoms between the two magnetic ions. And typically, these are halide ions. X is halide, so either chloride or bromide. And then the metals in our cases is typically copper. So in the bi-halide bridge, there's only one halide in between the two magnetic species, and so the only two parameters that we're really looking at is the distance between the magnetic ion and the non-bonding interaction between that and the halide, and the angle that it creates between all three atoms. In the two-halide bridge, there's an additional parameter, the dihedral angle, that's created by the lines that you can draw through the metal halide bonds on either side. So maximum antiferromagnetic interactions have been observed when the angle between the three atoms is 180 degrees, and the dihedral angle is either 0 or 180 degrees. So those are ideal conditions. So why choose copper? Copper has a D9 configuration and a nearly quenched orbital angular momentum. So thus the magnitude of the magnetic interactions is due almost entirely due to the spin of the electron, which is spin a half in this case. So a little bit more on how we're actually designing these materials. We've developed a family of compounds known as 5-sap compounds, where S is any substituent in the 5 position of 2-amino-pyridinium, the cation. And the substituents that have successfully created these 2D layers are the chloride and the methyl. I'll be focusing on the methyl group. The main problem with these materials is the inter-layer distances are too close to constitute a truly 2D material. So we have the distance between the sides of the square, you can imagine, are 4.5 angstroms, but the distance between the layers is only 5 angstroms. So we have a 3D ordering temperature of about 3.8 angstroms. This is the tetrabromocuprate compound. When you switch to the chloride, the interactions are a little bit weaker, and also the 3D transition temperature is a little bit lower. This is a function of the distances haven't really changed between the size of the square, but the distances between the layers it's increased a little bit, so that also has decreased the temperature of the transition. This is just a crystallographic representation of the chloride. The chloride and the methyl compounds look exactly the same. So, with this goal in mind, we want to just manipulate the 5 substituent here just a little bit. And we want to exchange the hydrogen atoms for fluorine atoms. Why are we doing that? The fluorine atom, van der Waals radius is about the same as the hydrogen atom. It's a little bit bigger, but the main thing that we're trying to affect here is the electrostatics of the substituent. So the idea here is we're actually going to push these 2 layers apart using electrostatic interactions. Another way we could have done the same effect is using sterics. So we could have extended this chain using an ethyl or isoprop or maybe even a tert-butyl. But those materials are a little bit more expensive starting materials. So I'll go ahead and just jump right into the synthesis of the first compound that I made. The picture of it is right up here. It's yellow compound little yellow crystals, and they're actually kind of bizarre. They're triangular when they crystallize, and I've never actually crystallized triangular crystals before. So it's a very simple reaction scheme. You react a pyridine compound in a 2-to-1 ratio with the metal halide and an aqueous solution with a little bit of acid, and you create this over a slow evaporation of the solution. After a couple of weeks, you get these beautiful crystals. This is just sort of in the IR of the final material with a close focus on the NH bend of the pyridinium ring. So we have indeed protonated this ring. And the CHN data agrees with the composition of the final product, which is good. So then the X-ray single diffraction data, which we collected over in New Zealand, Dr. Jan with Rockire collected the data for us, and then I personally solved the crystal structure with help with Professor Turnbull. And so this is the picture that we get. This is the asymmetric molecular unit. So here are the 2 rings on either side of the tetrachlorocuprate. Just looking at the geometry around the metal center here, we wanted to we took a continuous symmetry measure, which is essentially you take the difference between an idealized structure, let's say the tetrahedral structure, and you take the difference between that and the atomic positions of the atoms here in the crystal structure, and the difference will give you an S value where the S values closer to 0 are closer matched to that particular geometry. So you have to do the measurement for each individual ideal case. So we did it for a tetrahedral geometry and a square planar geometry, and the square planar geometry gave it gave a value a lot closer to 0 than for the tetrahedral case. So this means that it is indeed a square planar compound. It's not the distortion of around the copper is not uniform, however, as you can see by the 2 largest angles. So and then this is just a list of the hydrogen bond. There's one hydrogen bonding. There's one very strong hydrogen bond between the amino group and the tetrachlorocuprate group, which stabilizes the overall structure. So how do the anions pack? This is the most interesting part, actually. So this is where the magnetic species lie. This is where the copper lies. So how do these actually arrange themselves? Well, they dimerize, and the dimers stack along the b-axis of the crystal. So the distance between the 2 dimers is about 2.9 angstroms, and then the distance between the dimers here along the b-axis is about 3.9 angstroms, so a little bit longer. So we expect a little bit stronger exchange between the 2 units in the dimer than across the dimers here. So this is an example of a spin ladder, or at least we expected it to be a spin ladder. So what does the magnetism of these say about this material? And well, first of all, we want to take a quick look at the packing. This is just to show how isolated the the ladders are from each other. You can see this zigzag chain of fluorine atoms separates the two ladders from each other, and the distance between the ladders is about 5.9 angstroms. So they're quite far apart, and we expect very little 3D interactions. So what does the magnetism say? Well, we took the variable temperature magnetic susceptibility data. As you lower the temperature, you reach a maximum in Chi at about 10 Kelvin, and then after 10 Kelvin, it drops towards a value of 0. So this is indicative of a singlet ground state, so a spin gap compound. So this could mean that it could be either a dimer, or an alternating chain, or a ladder. But based on the crystallographic data, it makes more sense to be a ladder. But I fit it to both parameters using a dimer with the Curie-Weiss model, but we have to be careful because a Curie-Weiss model with the Curie-Weiss correction of greater than 5% is an invalid model, so we have to make sure that we don't use invalid models when we're describing the data. But so when we do model the behavior this way, we get a Curie-Weiss constant of about 15% of the dimer interaction. So this is an invalid model, and the only valid model we can match to the data is the strong model. So that's about 14 across the rung and about 3 Kelvin across the rail. So this is a strong rung. Just a little note on the magnetic impurity, that this is just an estimate, and usually the experimental paramagnetic impurity is around 2%. Okay, so then I'm moving on to the tetrabromo cuprate synthesis. So again, the synthesis is rather straightforward. It's about the same scheme as before, just reacting the two components in a 2-to-1 ratio in an aqueous solution with a little bit of acid, slow evaporation over a couple of weeks will give you the crystals, red block-like crystals. And so, and again, we can see the protonation of the pyridinium ring was successful. So, and the composition agrees with the final product. So what happens when you look at the single crystal X-ray diffraction data? Again, I saw this the structure, and we can see that the geometry around the copper is now a distorted tetrahedral environment with a mean trans angle of about 132 degrees. There are several weak hydrogen bonds that stabilize the structure, but nothing really of importance to note. At least in the hydrogen bonding. So when we look at the stacking of the anions, what do we see? We see a really exciting structure, actually. We see a honeycomb, and it's not a uniform honeycomb, it's a distorted honeycomb. So you can see the 6 points of the hexagon here, so 1, 2, 3, 4, 5, 6. But again, it's distorted. You get only 2 halide bridges in this compound. And we've got reasonable distances to expect moderate exchange across the metal centers here. In 3.84 angstroms, we've had materials that have very moderate to strong exchanges at these distances, and the dihedral angles are ideal. The only thing that is not ideal is the angles between the atoms, and they're less than ideal. But other than that, these you would expect, or we expected, to have moderate exchange or strong exchange across these metal centers. And what does the data tell us? Well, the variable temperature magnetic susceptibility data is rather disappointing. As I've plotted here also the chi-t plot on the same graph. So the chi is the red line here, and then the graph without the line is the chi-t plot. So as you lower the temperature, there's no change in the chi-t plot until you reach about 10 Kelvin, and finally you see a turnover in the chi-t. And this is indicative of an anti-ferromagnetic interaction, but it's very weak because the transition happens at a very, very low temperature. There's no characteristic turnover in the chi-t plot, so chi versus t plot. So you can model this however you please, actually, because all the models look like this before they have any characteristics. So you can actually fit it to an antiferromagnetic chain, get weak constant of 1 Kelvin, a dimer, a little bit stronger, 1.7. Strong models, that's actually really interesting. You actually get an ferromagnetic exchange across the rail, and this doesn't really make sense at all. But and then you get again an anti-ferromagnetic exchange of -2.7 across the rail. But this is just showing that you can model to anything you want, and it'll fit the data. They're actually all right on top of each other. You can't really tell from this picture, but there are 3 lines here, and they're literally the same fit in terms of the R squared values. Moving on to the synthesis of what we call the neutral compounds, neutral in the fact that we did not protonate the pyridine ring. We reacted the metal halide and the pyridine ring in a methanol solution. Slow evaporation gave us these 2 compounds. The dichloro copper compound crystallized as light green rectangular prisms, pictured here. They're very small. And the dibromo copper compound crystallized as dark red flocks. They're not red until you shine a light through them. They're actually kind of brownish if you just look at them at ambient light. There are very odd things going on in the IR. A full interpretation of the IR hasn't really been done yet, but it's a shift in the NH2 symmetrical stretch to about 25 reciprocal centimeters. And this is a rather bizarre shift, and I'm not really entirely sure why that's going on. But everything else agrees with at least the starting material. You don't change the starting material too much when you coordinate the copper to the pyridine ring. Or at least that's the theory. Okay, so what is the magnetic susceptibility data? Why don't I have any X-ray crystallographic structure information on this? Well, there are a lot of problems with the crystal structures, or with the collection of the data. Actually, they're not both of the materials are not single. In the case of compound 3, there's actually significant twinning occurring in the compound. So there's actually 3 components in one single crystal. So, but we can deduce, at least with preliminary data, we can say that it is a dimer. And so we modeled it as such in the magnetic susceptibility data. So that's this red line here. There's a singlet ground state, as you can see, at the moment dives towards 0, just like in the latter compound. And if you model it here, you get a constant of about 6.2. Now we don't have any data, structural data on compound 4. The crystals are just not single, so that's a problem. So we're going to need to try and see if we can grow singular crystals of this material to actually get some structural data. We cannot deduce anything from the magnetic susceptibility data. There's only a very small hump here for the turnover in chi versus T. So there's no real structural characteristics that we can deduce from this sort of plot. So we're going to really need some structural data to see what's actually going on in those compounds. So some conclusions of what we can draw from these compounds. This is very exciting. We stumbled upon a strong rung ladder, so we can add that on to the other ladders that we've studied. We've now studied, I think, 16 of the 20 compounds that have been discovered thus far. So for whatever reason, we tend to be the ones that discover these ladder compounds. I'm not really sure why, but we do. So we're going to go ahead and go ahead with a mixed halide system with this ladder compound. We're going to dope the ladder with slowly adding in bromide ions and see how that affects the magnetism. Making sure that we pay attention to the structure as well, because tetrachlorocuprate is very different in structure to the tetrabromocuprate. And with that, we discovered serendipitously this distorted honeycomb structure. We were really excited that we were going to see some really exciting magnetism with this material, but it turns out that the exchange is just too weak to warrant any further study. So in terms of the neutral compounds, we just need better single crystal diffraction data, and to actually deduce what's actually going on in those materials. And with that, I would like to acknowledge Professor Turnbull and Professor Villani for allowing me to do all this research for the past year and a half and putting up with me and all my questions. And also Dr. Jan Bukaira for collecting the X-ray crystallography data. And then, of course, my main inspiration, my father, who unfortunately passed away 2 years ago due to cancer, but he's been a continued inspiration to me in both my research and in my study of science. And I'll keep him in my heart as I go on to graduate school in Chicago. I would also like to thank members of the Turnbull-Villani group, the opportunity that I got with this Bickman Summer Research Internship Grant this last summer to continue my research, and of course family and loved ones and you audience for paying attention to this.